from New Prince Shri Bhavani College of Engineering and Technology. I welcome you all for the international webinar on Knowledge 4.0, Software Design Patterns and its Uses, organized by Department of Information Technology. To attain knowledge, add things every day. So to gain knowledge, I welcome our chief guest, Mr. Ashok Natarajan. Welcome you, sir. It's my privilege to welcome our chairman, sir, vice chairman, sir, director, sir, principal, sir, my dear colleagues, all heads of the department, students. I welcome you all for this webinar. Now, I would like to have Ms. Ushra Nandini, Assistant Professor, Department of IT, to share a few words about our college.
Good afternoon to all. Our college, New Prince Bhavani College of Engineering and Technology, established in the year 2008, is affiliated to Anna University and accredited by NAC and ISO 9001-2015 with excellent grade. Our college offering many courses like computer science and engineering, civil engineering, electronics and communication engineering, electrical and electronics engineering, computer application and information technology. Our college has multi-story buildings with spacious classrooms and well-equipped laboratories and library which caters to the need of the undergraduate and postgraduate students, research scholars and the faculty. A full-fledged transport department functions in our college with buses to provide transport facility to students and staff from various places. We also provide excellence and separate hostel facilities for both boys and girls, and admission is done as per the norms of Anna University, Chennai, and Government of Tamil Nadu. We also have various centers for enter, quality management, career guidance, placement and training, research and innovation, and Tech Super Hub, which helps to enhance the students' knowledge. Our college provides the best technical education and with placement center functioning in the campus. The very active placement center serves as a foundation for many careers by guiding students in right direction through continuous counseling and arranging for campus recruitment. The center creates a meticulous database and assists the students in getting placed in national and multinational companies through campus recruitment. We have successfully produced 91% placement in core companies like TCS, CTS, HCL, Infosys, and so on during the academic year 2019-2020. So when you step into the campus, you can feel beautiful ambience filled with our dreams, which will definitely come true. We provide enormous scholarship schemes for meritorious students by waiving of their tuition fees. We provide 100% free education for poor and deserving students. Apart from excellent academic track with various mission and vision goals, we also concentrate on several value added courses and certificate programs. We also stimulate students to take part in sports and cultural activities. We also encourage students to participate in workshops, seminars, conferences, and so on. Our aim is to reach and sustain high level of quality standard in terms of best academic process, research activities, center of excellence, advanced educational value added training and coaching, and better placement support. Thank you.
Thank you, ma'am. Now, I would like to introduce our chief guest, Mr. Ashok Natarajan. He completed his bachelor's from Shri Krishna College of Engineering and Technology, Coimbatore. Then he did his Master of Science in Electronics Engineering from Nottingham Trent University, UK. After that, he did his another Master of Science in Sensor System Technology from Hochschule Karlsruhe, Technik and Wirtschaft, Germany. At present, he is working as a software developer in Biosimulation Technology, GmbH, Germany. He deals with developing and maintaining a management tool for distributed components in virtual test drive, centralized configuration tool for distributed components in VTD, software for both front-end and back-end in Linux with C and C++, and ROS integration for VTD. I welcome you, sir. It's over to you, sir. Sir?
So yeah, thank you for the introduction, Ms. Karthika, and thank you for inviting me to do this seminar. So yeah, and I also thank everybody who was attending the seminar, and also thank all the faculties and all the members of
Can you be a
the.
little bit louder?
Yeah. So can you hear now?
Okay.
Is it fine?
Okay.
Yeah. Okay. Yeah. So I thank everybody who's attending today, and I also thank Ms. Karthika for inviting me and having invited me for this presentation on design pattern and its users. So yeah, I will start sharing my screen now. So to start with this topic on design pattern and its uses. So before going into this topic, so mostly I'll be talking about this design patterns and uses based on C++, but the scope of design patterns is not limited to C++ alone. It can be used for all the programming languages that that has the scope in OOPS or object-oriented programming. So to start with what I will be talking today, so I will, before going into the actual design patterns, I will be talking a little bit about the overview of object-oriented programming, and then I will talk about the types of design patterns and its uses, and I'll be also talking about some examples, which is all of them are in C++, and I will come to the conclusion once I have touched on all these topics. So to start this seminar, I will start with the object-oriented programming and the four pillars of there are four pillars of this object-oriented programming structure. So they are actually data abstraction, data encapsulation, inheritance, and polymorphism. So these are the four building blocks of any object-oriented programming structure. Without these building blocks, object-oriented programming doesn't exist. So to start with data abstraction, so the textbook definition of data abstraction is it refers to providing only essential information to the outside world and hiding their background details. So this is the textbook definition of data abstraction, but what it actually means is, you can see this from an example. Yeah. So here we have a class called adder, which has a public constructor and a public function called add number, and we have a private data member total. So so we have hidden the data private data member total from the outside world. We have only is someone using their speaker, because I can hear my voice back.
You can continue, sir, now.
Okay, thank you. So we have hidden the data member from the outside world, and we have only exposed the functions that are actually needed to the outside world, and we keep the implementation of the other all the unnecessary things for the outside world completely isolated from the outside world. So this is how we do data abstraction. So to move on, we have the another most important concept, which is data encapsulation. So the textbook definition for data encapsulation is It's defined as wrapping up the data and information under a single unit. So in programming concept, it's binding together the data and function that manipulates them. So what does that mean is, so we keep all the data and the functions and all the setters and getter methods under a single umbrella. So we keep all these encapsulated in a single block, so single object, so that we don't have to rely upon information or data which are coming from the anywhere outside of the object. So we are completely encapsulating all the data and its data members and the functions that act on the data members completely inside an object. So to see this from an example, so here we have a class called encapsulation. So we have a private data member, X, and we have two functions. One is the setter method and the other one is the getter method. So here we instantiate an object of this class.
Ashok,
Yeah.
can you be a little bit louder?
Okay. So is it okay now?
It's okay now.
Okay. So yeah, coming again, we have an example class here called encapsulation, and we have a private data member, which is the X, and we have a setter method, which is the set, and we have a getter method, which is the get. So in the main function, we instantiate an object for this class, which is the encapsulation, which is called the OBJ, and we can set this member from using the setter function, and we can retrieve the variables. We can retrieve the information stored in this variable from also using this getter method. So this is an object which is completely encapsulated. The data member is also inside that object, and also all the processing functions are also inside that object. So you don't need any other functions from outside of this class to deal with it. So this is completely an example of how we encapsulate all the members inside a single object. So to move on, the next important concept of object-oriented programming is inheritance. So the definition of inheritance is that the capability of a class to derive the properties and characteristics of another class is called inheritance. So to see from this image, we have this vehicle class, which is the base class. It has three functions: fuel amount, capacity, and apply brakes. So if I want to create three different classes for defining a bus, a car, and truck, all these classes have common functions, namely the fuel amount, capacity, and apply brake. So what we can do is we can define a base class, which is the vehicle class, and we can derive the bus, car, and truck from this base class, and we can operate, and we can use these subclasses to derive from the base class and operate on these subclasses. To see this example, so we have this code here. So this is a base class vehicle, which has a member registration number, and also it has functions like start engine, accelerate, and apply brakes. So this is the base class, and we have three different derived classes here. One is the car, and the other one is the bus, and the other one is the truck, which is all inherited from this base class. So all these implementation which is available in this vehicle will also be available in the car, in the bus, and also in the truck. And this has internal members called year made in the car, and passenger capacity in the bus, and truck in the model number. Model number in the truck. So these internal data members will be available only within this subclass, but this member and these functions will be available in all the base class, and also the subclasses which are derived from this base class. So in this main, if I create an object of car named Corolla, I can instantiate this registration number and year made. So registration number comes from this vehicle base class, and the year made is a private variable that is specific to this subclass car. I can also call this start engine and accelerate, which comes from this base class. So if I have to create an object for bus, so I can operate on two different variables. One is the registration number and the other one is the passenger capacity. And also I can operate on all these functions from the base class, from the bus subclass. This is the concept of inheritance. And moving on, we come to the last concept, which is polymorphism. So polymorphism in Greek is is a Greek word polyk, which means many forms, having many forms. So polymorphism can be grouped into two different categories. One is compile time polymorphism, and the other one is the runtime polymorphism. So compile time polymorphism occurs with method writing and operator overloading, and runtime polymorphism occurs with virtual functions. So basically polymorphism happens when we use a class which is used to inherit from a base, when we use derived classes which used to inherit from a base class. So the example for polymorphism is, so here we have a class which is a base class, and we have a derived class which is derived from this base class. So in the main function, I create a pointer to the base class, and I create an object for the derived class, and I can assign this object to the base class. So if I call this function print, so this print will call the function from the derived class and not from the base class, because this is a polymorphism. So we assign the value of a derived class to the base class. So this base class, even though it's a pointer to the base class, it will operate as a derived class. So this print is a virtual function. So this is a runtime polymorphism. The show is not a virtual function. So the polymorphism happens at the compile time. So this is the concept of polymorphism. So we have covered the
Sir,
four. Yeah.
sorry for the interruption. Can you be a bit audible? You're not audible, it seems.
Okay.
A bit louder.
Yeah, no problem. So yeah, till now we have seen the four different building blocks of object-oriented programming language, specifically using C++. But the object-oriented programming is not limited to C++ alone. You can use this in Java, in Python, and many other available programming languages have the object-oriented programming features. So to move on to the actual topic of today, the design pattern. So what is a design pattern? A design pattern is a general credible solution to commonly occurring problem in software design. So in software design, we have a lot of common problems which can be addressed using design patterns. So design patterns is using design pattern has a lot of advantages. We can create reusable code. We can create clean code using following the design pattern strategies, and also we can create a very good clean code that can be useful to help develop in the further process. The development will be easy if we follow the design pattern strategies, and also it can be it's really easy to communicate with other developers on how to design and how to write the software. So it's always a good idea to know the design patterns and to write code based on available design pattern strategies. So design pattern, as I said earlier, is language neutral. Every language that has every programming language that has the feature of object-oriented programming can adapt to the design pattern strategies. So if you know C++, if you know Java, if you know Python, whatever, you can use this design pattern. So design pattern is just a designing principle. It's not specific to any single programming language. So where did this design pattern start from? So the design pattern started from the Gang of Four. So the Gang of Four is the four American scientists: Eric Gamma, Richard Helm, Ralph Johnson, and John Willisides. So these were the four guys who came up with the idea of design pattern. So they wrote this book on design patterns, which was released in 1994. So from then on, the design patterns is available for all the whole world. So most of the development process in the software happens with the help of design patterns. So the Gang of Four design patterns, we have 23 different design patterns from the Gang of Four book. So this is the classic design pattern. So there is also a lot of modern design patterns, and we also have a lot of undocumented design patterns. But the 23 design patterns documented by the Gang of Four is the classic design patterns, and knowing that is more important and more helpful in the software field. So moving on with the design pattern, we have 23 different classic design patterns, which is grouped into three different types. One is the creational design pattern, the second one is behavioral design pattern, and the third one is the structural design pattern. So we have 5 creational design patterns and 7 structural design pattern, and the remaining are the behavioral design pattern. So what is the creational design pattern? So the creational design pattern provides designs to create new objects. So it gives us the design to create new objects. And the structural design pattern actually gives us design to gives us the design to write software for defining the relationship between different objects. And the behavioral design pattern gives us the design to write software for the communication and interaction between different objects that are instantiated in the code. So yeah, obviously I cannot cover all the 23 design patterns today because of the time constraint. So I will be discussing about 7 different design patterns today, which I feel is a bit more important than the others. So I'll be talking about Singleton design pattern, factory design pattern, strategy design pattern, observer design pattern, builder design pattern, adapter design pattern, and also chain of responsibility. So these are much more important from my point of view than the others. So I'll be discussing about all the 7 of them today. So to start with, we have the Singleton design pattern. So the Singleton design pattern is the most widely used and very well-known design pattern that's very much famous in the software industry. The textbook definition for Singleton design pattern says that it defines a class that has only one instance and provides a global point of access to that instance. So what does that mean? So it means that if we take a real world example, if I have a banking software that maintains the account balance of every account that the bank has. So if I have an account with the bank, and if I go to a branch of the bank, and if I deposit my money in one branch, and if someone uses my ATM card, if someone from my family uses my ATM card and withdraws an amount from an ATM center somewhere else from the city. So both of these, if I deposit 1,000 rupees, and if someone withdraws 1,000 rupees from my account, so my account should stay stable. It should not. So I deposited 1,000 and someone withdraw 1,000, so my account balance should stay the same. But what if we create 2 different objects for depositing and withdrawing? So it will create a confusion, and it will create a lot of junk and unreliable data. So to avoid this, we have to make sure that at any given point of time, there is only one instance of the class created. So if there is more than one instance of a class created, then this is not an acceptable solution for this particular case of banking software. So they always have to maintain this constraint of having only one particular instance of that object at any given point of time. So how can they do it? It can be done using following the singleton design pattern. So the UML diagram for the singleton design pattern is as shown in this slide. So in this, when we create a software using the singleton design pattern, we we declare the constructor as in the private, and we give access to a get instance method that will return the instance of the object of the class object that is already being created, or it will return a new instance if there is no object which is already existing. So to look at this in more detail, we will see this through an example. So I have a class here which is called singleton class. And as you see here, the constructor is declared in private section. So there is another static instance of this singleton, which can be accessed with this get instance method. So from the main function, we create a pointer to the singleton class. We create a pointer of the object of the singleton class. And we use this get instance method to instantiate this singleton object. So what this get instance method will do is it will check if there is already an available instance of this singleton class. If there is an already available instance, it will return the already available instance. If there is no instance which is already available, and if this is the very first time that we are creating this object, then it will create a new singleton object, and then it will return that instance. So in this way, we make sure that only one instance of this object is available at any given point of time, so that we don't create multiple copies of the same class, and then we end up creating junk data and unreliable and unusable data at the end. So this is how the software industry solves the problem of avoiding creating multiple copies at unwanted times. So that's all about singleton design pattern. So to move on, we have the next design pattern is the factory design pattern. So factory design pattern, the definition for the factory design pattern is it's a creational design pattern that provides an interface which encapsulates object creation and lets the subclass decide what objects to create. So for example, if I have to write a software for a toy factory, and if the toy factory produces 3 different types of toys, one is the bus, one is the car, and one is a plane. So the working of this factory will be the same. So to create a car or plane or any other toy, the process is the same, but the output and the parts and the assembly is different, but the creation process is the same. So in this type of scenario, we can use this factory design pattern to create a better software, and with less code, and which are which are in a way very well written, and which can be used for further development and processing. So the UML diagram, which for the factory design pattern for the So yeah, someone raised their hand. Do you have a question? Okay, to continue with factory design pattern. For the example which I was discussing a few seconds ago, so this is a abstract class for a toy, which has the functions prepare parts, combine parts, assemble parts, apply label, show product. So and we can derive these classes from the base class, from the abstract base class toy. So here I have a car object, here I have a car class, here I have a bike, and here I have a plane, and we have this toy factory. So the client actually gives the input on what toy he wants. So if the client requests the toy factory to produce car, so the toy factory will then instantiate production of the car toys. So if the client requests to create a bike, then the toy factory will start the production of the bike toys. And if the client requests for plane, then the same will be done for the plane toys. So to see this with a code example, so we have, so this is the base class for vehicle. So we have the abstract base class where we have this print vehicle function and the create vehicle function. Using the enumeration of, we have three different types of productions in this example. We have three different types of productions for the vehicles. One is two-wheeler, one is three-wheeler, and the other one is the four-wheeler. So we have the abstract base class vehicle, and then we have two-wheeler, three-wheeler, and four-wheeler, all deriving from the vehicle base class. And all these subclasses will create objects based on their requirement. So here is where the client gives the so the client passes the input of which classes to create, which object to create. So from the main function, we create the client, and then we call the get vehicle function. So once the client is created, here the code, we have hard coded that the client is already requesting a three-wheeler. So the client is already requesting a three-wheeler. So this information will be passed to the function. And then we are already producing the three-wheelers here. And then once the print vehicle function is called, then then the code will start printing out I am three-wheeler. So that's how we can write code using the factory design pattern to create objects of having similar processing state, but different processing functions. So we can couple all of them. We can write source code that is loosely coupled so that we can create different types of objects reusing the same source code without writing a lot of repetition in code, and without wasting a lot of resources. We can loosely couple this source code under this factory design pattern and create objects which are according to the client's request, which is in a way very easy and helpful in software industry. So to move on with the next pattern, we have the strategy design pattern. So this is a very simple design pattern. So the strategy design pattern is a behavioral design pattern, and the definition for the strategy design pattern is that it's a behavioral design pattern that lets you define family of algorithms and encapsulate each one and make them interchangeable. Strategy lets algorithm vary independently from the client that uses it. So what this definition means is we can see it from a real world example. So we all have different word processing softwares, different word processing tools like the Microsoft Word or Microsoft or many other word processing tools. So we can save the files in these tools under different extensions or under different file types. Like we can store a Word file as a PDF, as a document, as a rich text file, RTF, as ODF, or different formats. But the basic functionality of this it remains the same. Like you open the Microsoft Word and you edit the document, you change the documents, and then you select save, and then and as a last step you select which file type you wanted to save. So all the functionality remains the same until the end, where you define which file type you need the document to be saved in. So only at the last process, you define a strategy for the saving of the document. So if we see it from the UML diagram for the example we just discussed, so this is the client. So and the client is communicating to the context, and then it's injecting the strategy. So it's injecting which file type it wants to save the file in. So we have an interface. We have an interface that has two different implementations. So consider this implementation one as a PDF file type, and the implementation two as a doc file type. So the client sends the strategy, and the strategy, if this client wants PDF, then we execute this block. If the client wants a document format, then we execute this block. So if you see this from an example, so this class strategy is the interface here, and the context is what we see this block in this block. And we have two different implementations. One is the concrete strategy, and the other one is the concrete strategy A. One is concrete strategy A, and the other one is concrete strategy B. So we have the client code here. So we create an object of the context, and then we pass in a concrete strategy A to this to the context object we created. So once we come to this constructor, it accepts a strategy object. So what it does is it saves this strategy object in its member variable strategy. And once you are passing this concrete strategy A, then if you call this do some business logic function, so this do some business logic function is defined from the context. And this function will call the do algorithm function of the strategy you passed. So the do algorithm is an a virtual function here, an abstract virtual function here. And these two different classes, concrete strategy A and concrete strategy B, are derived from the strategy class. So if you see this UML diagram, this interface is is the base class for this implementation one and implementation two. So we have the interface here, and we derive the strategy. We derive this concrete strategy from the strategy class here, and we derive the concrete strategy B also from the strategy class here. So we have an abstract function here called do algorithm, which is overwritten in these two classes. So this is overwritten by this chunk of code, and the do algorithm in this class is overwritten by this chunk of code. So what we do here is we create a context object, and then we pass a strategy. So if referring to the last example which we were discussing, so if you just open a context and you pass in the file structure you want to save in. So if you pass here in if you pass here, this is considering this as a PDF. If you pass the strategy as PDF, then we go here, and the strategy here is saved as what you sent. So because in the constructor we pass in the strategy, and this strategy is stored in this member function. And once this do business logic is called, it will call the do algorithm of the strategy which we passed in from the constructor. So if we pass in the concrete strategy A, this chunk of code will be called for do algorithm function. So here, considering the example, if we want to save it again, it's the same file again in a different format. So we call this set strategy function. So in this set strategy, we can change the already sent strategy. So in here we send an object of concrete strategy B. So this will change the strategy defined in this in this class. And then once you call this do business logic again, then this do business logic function will call the strategy which you changed, that is the concrete strategy B's do algorithm function. So we come to here, and this chunk of code will be executed. So this is the strategy design pattern example, and this is how a strategy design pattern is implemented. So moving on to the next design pattern. The next design pattern we will discuss about is the observer design pattern. So observer design pattern is the textbook definition for this is a behavioral design pattern that lets you define one-to-many dependency between objects, so that when one object changes state, all its dependents are notified and updated automatically. So what does this mean? If we see this from a real world example, the social media is a real world example of an observer design pattern. So if you take either Facebook or if you take either Twitter, so if you are following someone in Twitter, if they make a tweet, you get a notification that they have made a tweet. If you are friends with someone in Facebook, if they post some status or post some photos, you get a notification that your friend has posted a status or your friend has posted a picture. So in a way that once you start following someone, or once you start becoming friends with someone in social media, in a way that you are observing them, so the observer design pattern notifies you once they have an update. So that's the real world example for an observer design pattern. So if we see this from a UML diagram, so we have the observer class here, and we have the subject here. So the subject has the functions register observer, unregister observer, and notify observers. So if someone wants to register as an observer, so if considering this as the social media example, if I follow someone, I register as an observer to their profile. So whenever they make an update, I'm notified from this notify function. I'm an observer, so I'm notified from this function that someone has posted a status. So I can also unregister from being an observer. If I unfollow someone, or if I unfriend someone, I'm already unregistered as an observer, so I don't get any notifications anymore. So we have this concrete observer A and concrete observer B that also has the update functions that is derived from this observer. So all the observers, this is a concrete observer that is derived from the base class of the observer, and all of them can register to the subject. And once there is a change in the subject, then they will be already notified about the change, so that they can do the further processing on this change. So to see this from an example, so we have this subject class here, and we store all the observers which wants to get notified about the change in this subject class using this vector. And we have this attach function here, which is the register function. And we have the set value and get value function. So once the new value is set in the subject, then all the observers will be notified from this notify function. And we have this observer class here, which is the base class of this observer. So we have the observer class here, and we have the update method in the observer class. And we have two concrete observers here. One is the division observer, and other one is the models observer. So these are derived from these this base class. So from the main function, we create an from the main function, once we create a object of the subject class, and then we create an object of the division observer. And this constructor expects two parameters. One is an object for the subject class, and the other one is an integer. So we create an object of the subject class, and then we pass it to this observer, constructor of this observer, and then we pass an integer value. And in a similar way, we create three different observers. Two div observers and one mod observer. So once we create this object, this is derived from this base class. So this is also initiated. This is a class which derives from this base class. So we save the subject in this in this member function, and we save the integer in this member function in here. And the next process is that it attaches to the subject. So this attach function is called. So the attach function, what does the attach function do is it pushes all the observers that want to observe the status of this subject class into this vector function. So once I create an object here, I go to the constructor here, and then I come to the constructor here, and I get attached in the list of observers. In a similar way for this, from here to here to here to here. And this one also from here to here to here to here. So all these three observers are registered, all these three observers are registered in the subject class, so that they will be notified once there is a change in this value variable. So here when we set this value variable as 12, so this value will be set in this member variable, and then the notify function will be called, and the notify function will call the update function for all the observers. So immediately we come to this place and this place, and we have two different div observers. One is having a value of 4 and the other one is having a value of 3. So here division is performed for the set value 12. So the output for this two will be 12 divided by 4 is 3, and 3 divided by 12 is 4. Sorry, 12 divided by 4 is 3, and 12 divided by 3 is 4. So the output will be print. And for this object, we come to this update function, which will take a modulus of 12 divided by 3, which is 0. And now we change the value again. Now we change the value to 36. So once we change the value to 36, then the notify function will be called again, and the notify function will call the update again for all the three observers, and all the three observers will again act on the new value. So this is an example for how we implement the observer design pattern. So moving on, the next design pattern is the builder design pattern. So the definition for builder design pattern is it's a creational design pattern that lets you produce complex objects step by step with the same building process. So to see this from an UML point of view, we have this director class, and we have this builder class, and we have concrete builder and the product. So this is the end product, and this is the class which communicates what is the end product that needs to be built. So we can first see this from a source code point of view, and then we come to the UML later. So this is the product that needs to be created. And here we have an abstract builder function and a builder class. And here we have the concrete builder class. So the concrete builder class has produces three different parts. One is part A, part B, part C, and it returns the get product from this function. And the other class is the director class. So the director class, what it does is it has two different functions. One is build minimal viable product. That is, it produces a product only with part A. And we have another full featured product that produces all the three parts, part A, part B, and part C. So this is the client code. So the client, what we do here is we create a director function from the main function, and then we pass this director object to this client code. So what is happening in the client code is we create an object of this concrete builder, and we pass it to the director. We pass this to the set builder of the director. So what happens in this set builder function is this this new concrete builder, which we have defined here, is passed into this director's set builder function. So it uses this concrete builder to build all of the new products. So once you call this minimal viable product, it produces a product only with product A. So if you call this director with full featured product, then it produces a product with all the three parts. And also you can create custom products from this builder. You can call just product A, product B, or product C, and then you can create all the products customly without the help of a director. You can do this on your own. So now if we go to this UML diagram, we see this director here. So this is the director. So the director has an object of the builder class. So the builder is here and it is an abstract class, and the concrete builder is, it derives from the builder class. So the concrete builder has an instantiation of the product class. So the product class is defined here. So this is how the whole pattern and the whole example is coupled. So we call the director instantiates a builder, and the builder produces the products according to the client code. Sorry, the director produces the product according to the information from the client code, and it can be and the product is printed from the product function. So at the end of the using this design pattern, you can use the director to configure the product you want to build. So from here you produce a product which has a minimal information, and here you produce a full-featured product, and also you can produce a custom product according to the user's requirement or the client's requirement. So that's how this code is coupled, and that's how we implement the builder design pattern. So to moving on to the next pattern is adapter pattern. Adapter is a structural design pattern that allows objects with incompatible interface to collaborate. So this is personally my favorite design pattern, because to define this from a real world example, I have an image of an adapter. So what does this adapter do? What is the function of this adapter? So if we have an incompatible socket, so if we have a product which is shipped from the US or from Europe, so it has a different plugin point which is not compatible with the plugin socket in India. So we have to use an adapter to convert the voltage in the Indian socket to the product which we are using, which is shipped from the US or from the Europe. So that's what is the functionality of an adapter. In a similar way, in the adapter design pattern, if we have a software that communicates with a Windows system, and it derives the files from the Windows system. If you have a similar software, and if you want that software to work in Linux, so it will not work directly. You have to use an adapter to make it work with Linux. So you have to create an adapter that will adapt to the implementation of the Windows system, which will convert it to the Linux. So to see this from the UML diagram, we have a client and we have this end result, which is adapter. So the adapter has a function called specific request, but the client is sending a request, the target function. The target only has a function request. So this is incompatible here. So this request, if the request directly calls the adapter, this is incompatible. Here we have a request and here we have a specific request. So we create an adapter here that will adapt to this specific request. So it will adapt this specific request, and then it will process it, and then it will provide the request that is needed by the target, which is sent from the client. So to see this from this example, which is so here we have three different classes. One is the European socket interface. This is an abstract class of the European socket interface. And what is the European socket interface? The socket in the European socket interface has a voltage of 230 volts, and live is 1, and neutral is -1, and earth is 0. So here we have another class for a US socket interface. So this is an abstract class. We have voltage 0, live 0, neutral 0. But we don't have a socket for the US socket interface because we are in Europe. Consider we are in Europe. So considering we are in Europe, we don't have a socket interface for, we don't have a socket for US. So, but we have a kettle. We have an electric kettle that is shipped from the US, and that will only work with a US socket. So how will we make it work? We are creating here an adapter class. So what does this adapter class do? It has an interface, it has a variable for member variable for the socket, European socket interface, and it has a plugin function. In a similar way, the kettle also has a member variable for US socket interface, and it has a plugin function. So how do we make this work? We'll make this work from this main function. So we create an object for the socket. So we create an object of this socket. So the socket has a voltage of 230, and it has a live of 1, and neutral of -1, and earth of 0. But we need a voltage of 110, and live and neutral and earth is normal. We don't need to change it, but we need to change the voltage. So how will we do it? So we create an object of the adapter pattern, and also we create an object of the kettle pattern. So plug in the adapter into the socket. So we use this adapter, and we call this plugin function, and we pass in this socket object to this plugin function. So once this plugin function comes to this socket, then it changes all the voltages from 230 to 110, and the live and the neutral will remain the same. So once you plug in, the adapter is plugged into the socket, it changes the interface. So now we can plug the kettle into the adapter. So once you plug in the kettle, you pass this adapter object into this kettle here. So the power supply will be 110 volts, which will be coming from here. So once you use this power for the voltage, then it will be less than 110 volts. So if it's more than 110 volts, the kettle will be on fire. If it's less than 110 volts, then we have a nice cup of coffee. So to explain this again, so we create a socket object. We create, oh, shit. So we create this socket object, and this socket object is initiated here, and then we create an adapter object, and then we create a kettle object, and we plug in the adapter into the socket. So once the adapter, the socket comes into the adapter's plug-in, then the voltage of the socket will be changed. And once we plug in the kettle back into the adapter, then we get 110 volts from this adapter, and then we have a nice cup of coffee, and our kettle is not on fire. So that's how we implement the adapter design pattern in real world. So in the last design pattern, which we'll be talking today, is the chain of responsibility design pattern. It's the textbook definition for this design pattern is it's a behavioral design pattern that lets you avoid the coupling of the sender of the request to its receiver by giving more than one object the chance to handle the request. Chain the receiving objects and pass the request along a chain until an object handles it. So to see this from the UML diagram, so the client sends a request. So this request is handled by this handler. So we have two different handlers, concrete handler and concrete handler 1 and concrete handler 2. So from the definition, so we are not tightly coupling the sender's request to the receiver, but we are giving all the handlers the option to act on the request from the client. So if any of the handler can process the request from the client, then that object can process it, and the others. So we create a chain of responsibility for all the handlers. So if one handler cannot process the request from the client, then it passes the request to the next handler. And if the next handler can process it, then it says, I can process it and I will act on it. If not, then it will pass it to the next handler. So that's how this chain of responsibility works in a chain manner, that different handlers are involved in here. So the client request is passed to one handler, and the handler which can process it will process it. If the handler cannot process it, then it sends it to the next handler, and in a similar way the chain continues until all the handlers have seen this request. If one of it can process it, then it processes it. If none of them can process it, then it replies the client that none of the handlers can process it. So there is some error from the client side. So to see this from an example, so we have this handler class, which is an abstract class here, and we have an abstract handler class that is derived from the handler class. So the abstract handler has the private handler method, private handler variable, and it has constructor, and it has this handle function. So this handle function is the important function we have to look into here. So this function will, if this is setting the next handler to the next handler to handle the request. If it's not processed, then then this sets the next handler to handle the request. So to see this, we have three different handlers here. So from the UML diagram, we had two handlers, concrete handler 1 and concrete handler 2. But in this example, we have three different handlers. One is a monkey handler, other one is a squirrel handler, and the other one is a dog handler. So the monkey handler, all these are derived from the abstract handler. So they all of them are replacing this string, overriding this handle function with their own implementations. So the monkey handler will process the request from the client, and if the request is banana, the monkey will eat the request. If the squirrel handler will process the request from the client, and if the request is nut, it will process it. If not, it will send it to the next handler. In similar way in here, if not, it will set it to the next handler. In the dog handler, if there is a meatball, it will eat it. If not, it will send it to the next handler. So from the client code, we have a vector of food, which has three different food. One is nut, and the other one is banana, and the other one is the cup of coffee. So in the main function, we create a monkey handler and a squirrel handler and a dog handler. And we set, so we go to the set next function. So we go to the set next function, and we set the next handler to, for the monkey, we set the next handler to squirrel, and for the squirrel, we set the next handler to dog. And then we create a client code with the monkey handler. So the client code accepts this monkey handler, and then it sends out the request, nut, banana, and cup of coffee. So this first request is the nut, and the nut will come to the monkey handler, and the monkey handler cannot process this, so it will send it to the next handler, which is the squirrel handler. The squirrel handler will process it because it's the squirrel handler's request. So it will say that I am the squirrel and I will eat the nut. The next object is the banana. It comes to the monkey handler. It can already process it. So it will say, monkey, I will eat the banana. The next one is cup of coffee. So it comes to the monkey handler. It cannot process it. So it sends to the squirrel. It cannot also process it. It sends to the dog. It cannot also process it. So So it comes back to the client, and the client says cup of coffee was left untouched. So we create another client code, another client code here with object squirrel. So the squirrel will come here. The squirrel is just connected to only dog. So this is monkey. So we send the monkey here, and monkey is connected to squirrel and dog. So the monkey, if we send a request to the monkey handler, then it sends to the monkey, and it's first processed by the monkey handler, and then to the squirrel, and then the dog. So here we create a client code with just the squirrel handler. So the squirrel handler will try to process it. If not, it will just try to send to the dog, and if both of them cannot process it, it will just leave it. So if we run this client code, this will only the nut will be processed. The banana and cup of coffee will be left untouched because the monkey is not there to process the banana. So we get the error. We get the message as banana and cup of coffee was untouched and nut is processed. So what is the real world example for this chain of responsibility pattern? So if we are using a web development, or if we are in ordering, if we are using some online ordering or online shopping, so we have to process a lot of requests and requests from the client side. So you have to process the login information of the client, and also you have to pass the payment gateway, and also you have to pass many other handlers before the order is processed. So in that scenario, if we write a tightly coupled code with if-else statements, that creates a whole lot of chunk of junk code, which is really not easy to maintain, and it creates a lot of bug. So if you create a chain of handlers to handle this request, so if this handler can process it, if processes it, if not, it passes to the next. If not, it passes to the next. In a similar way, if you create a chain of handlers, it's easy to process such type of scenarios where you have to process a lot of information, and creating whole lot of if-else statements is really buggy and looks so weird. So that's the real world example to use this chain of responsibility design pattern. So yeah, so I have come to the end of my presentation, and I will be I thank very much for all the people who are patiently attending this seminar, and also for all the faculty members and Ms. Karthika for giving me this opportunity. So if you have any questions on this presentation, I will be happy to answer them.
Thank you, Ashok. It was very informative. Now I would like to call Ms. Arijyoti, Assistant Professor, Department of IT, to ask few questions.
Good afternoon. Good afternoon all. We have so many compartments. First question: in what way these design patterns will be used in real time? So,
yeah, in
what design patterns will be used in real time?
Which design pattern?
All the design patterns, sir, will be used in real time.
Yeah, so yeah, I was explaining during my presentation that how we will use it in real time. So the first one is Singleton design pattern. Singleton design pattern is used in the banking softwares, and the softwares where there is a demand for only one object to be existing at one point of time. So if there is multiple objects existing at different times, then then there is a problem that we create a lot of chunk data, and we don't have a centralized information on what is processing in the banking software. So the Singleton design pattern is not just the scope is not just limited to the banking software, but for every place where there is there is a need to have only one single instance at given point of time, where there we use this singleton design pattern, and the factory design pattern is used in almost all of those factories which are manufacturing more than one type of product, and more than one type of product, and which has the production line is the same. So if you take a production factory of a BMW production unit, they produce different varieties of car, but the production unit is the same. So if they want to produce a sedan, then they just send a client, they just change the setting to use the sedan parts and sedan assembly line and sedan assembly unit to produce the sedan cars. And if they want to produce a SUV, then they change the client request to produce the SUVs. And if they want to produce hatchbacks, then they change the client side information for the factory design, for the factory's input. So that's the use of the factory design pattern in a real world scenario.
Thank you, sir. And the next question is, how is the bridge pattern different from the adapter pattern?
How is the which pattern?
Bridge pattern different from the adapter pattern.
I have not discussed about bridge pattern. I have only discussed about adapter and builder.
Okay, sir. Thank you. And
Okay.
The last question is, in what order would you describe a design pattern in its documentation?
In what order? So
Would you describe a design pattern?
Mhm.
Would you describe a design pattern in documentation? In what order?
In what order? Okay. So yeah, so it's defined in three different types actually. One is the creational and structural and behavioral. So in all the documentations for design patterns, even in the Gang of Four book, it's defined in these three types. So first one is the creational design pattern, and the next one is the structural design pattern, and the next one is the behavioral design pattern. So that's the types, because the creational design pattern is specifically for gives us the design principles for creating objects, and structural design pattern gives us specifically the design principles for relationship between objects, and the behavioral design pattern gives us the information for design principles for communicating between different objects. So so that's how it will be in most of these documentations, because first we create and then we structure and then we change the behavior.
Thank you, sir. Thank you for your valuable answers. Thank you,
Thank you.
participants, for your questions. Thank you, sir. Now I hand over the session to Karthika, ma'am.
Thank you, ma'am. Participants, feedback link is posted in the chat box. After filling the feedback form, you'll be getting your certificates. I repeat, your feedback link is posted in the chat box. And after filling the feedback, you'll be getting your certificates. Now we are at the end of the session, and it's my pleasant duty to propose the vote of thanks. On behalf of IT department, I would like to express our sincere thanks to our chief guest, Mr. Ashok Natarajan, for sparing his valuable time this afternoon during his busy schedule. I also wish to express my gratitude to our chairman sir, vice chairman sir, director sir, principal sir, for constantly motivating and encouraging us to organize webinars. I would like to extend my thanks to our HOD, Dr. S. Subburam, heads and staff members from other departments, and our IT department staffs and students for providing me an excellent support. Finally, I thank all the participants. Without you, this cannot be a successful one. Thank you all. Participants, kindly stay. There is a photo session. You can now turn on your video for photo. Participants, turn on your video for photo.
Yes, Karthika ma'am, you can wind up the session.
Okay. Thank you all.